possibly going to do in this sesh. So we're doing that thing where if you look so we're very concerned with linear threshold functions, right? Like these are like Boolean functions where you can represent them with a weight array and a bias, and we're trying to understand like in what ways can LTFs be different from each other, and it kind of seems like, well, you just talk about like the weight bias representation, and I mean it's kind of obvious, like if different. So anyway, what we're specifically doing is we're saying like, okay, we're canonicalizing the H out of, we're canonicalizing. So we're saying like zero bias. All of the weights are positive sign, and they are also sorted, like largest weight is in like the leftmost index location, and so we're the constraints on the representation. What can happen? And like it kind of turns out not a huge, I mean like less than normal, I guess, or whatever. So like let's look at this as an example, and then but then we have like an open question that comes from this thing. But let me explain this. So like each column, so we're in n equals 4, and I used ChatGPT to figure out how to label the rows with the binary strings. So yeah, so like the rows are the inputs, and then like like the purple is like -1 as an output, and the yellow is +1, or maybe it's 0, 1, it doesn't matter. And so what we have is for n equals 4, these are all of the canonical LTFs that are possible. There's only 3 of them. Modulo sampling error, because like I'm just I'm producing this by like random sampling of weights, and then figuring out what function the weights are computing, and then like keeping uniques. And right, so but yeah, like it's not that hard to interpret really what's happening, right? So like what it's saying is that it's saying that the weight corresponding to the leftmost index has to be the greatest weight. So what this first column is saying is like that weight, particularly the input corresponding to that weight, controls the output. And so like the first column is the input identity function for x sub 0. And but another way of saying that is that the magnitude of the largest weight is greater than the sum of the 3 smallest weights, right? And like that's a thing that could happen. But then if we go to the second column, what's happening in the second column is like it's saying like it's the same as this, except for this input 0, 1, 1 is a yellow, which means that it's like +1. So it means it's greater. Yeah, because I mean, like, the bias is 0. So anyway, well, what it's saying is that the sum of the 3 smallest weights is larger than the first weight, than the largest weight, right? And that's like totally a thing that can happen, right? Like, it's totally possible for that to happen, and it did. And then, okay, so then, like, what's going on with the second column? El column segundo. That means second. It's the same thing, and except it's saying yeah, right. It's saying like the sum of the largest weight and the smallest weight is less than the sum of the middle 2 weights. That's like totally a thing that can happen. Like, you can totally produce arrays of like 4 numbers where it's sorted, and the sum of the two, the largest and the smallest is greater than or less than the middle 2, right? And so I was kind of saying, like, if you just look at like canonicalized LTFs, where, because I mean, like, obviously if you have LTFs and they have like different sign patterns on the weights, and like different biases and stuff, it's like, yeah, you can get different functions. But I mean, like, there's kind of some sense in which those are all just kind of like geometric. But anyway, the point is that even if you fix all of those ways of making different weights, you still get this kind of game happening, where you're like, haha, like, are the smallest weights, the sum of all the smallest weights, larger or smaller than the sum of the, whatever. And but also it's more complicated than that, because a thing that happened here is, like, we randomly generated, I don't know, like 60,000 weights or something. And the thing that happened is that every time you had this happening, the x1, w1 plus w2, those are weights, larger than w0 plus w3, right? Every time that happened, you also had the bottom 3 being larger than the largest weight. And I'm trying to think, like, does that necessarily imply, let me move to my, so, like, if you have 0, 1, 1, 0, I think it does, but I'm not directly seeing what's happening here. It's greater than 1, 0, 0, 1. I'm saying, like, does that imply that 0, 1, 1, 1 has to be greater than 1, 0, 0, 0? And does this imply this? I mean, really, we're looking at the implication in either direction. So let's say, does it imply from the top inequality to the bottom inequality? Because Well, okay, oh, God. I think you can, like, if you can add the equations together, but do you want to? Well, wait, what's going on here? Okay, it's saying, okay, so to go from this to this, you add W sub 3 to this side, and you subtract W sub 3. So you're literally just moving W sub 3 from this side to this side. That can only make it smaller. I mean, yeah. Right. Because you're taking a positive value on the small part, and you're moving it to the large part. Right? So yeah, these two, this equation implies this equation? Yeah. I think so. It's not an equation, it's an inequation. I think, okay. Yeah. Right? Yeah. Okay. Good. So that's kind of a thing that's happening here, right? Like when you're looking at canonical LTFs, it seems like you have like two combinatorial phenomena. Yeah. You have just the general, like, which sum of weights is larger than which other sum of weights. But then you have these implications. Like we just saw that if you have this input is larger than this input, then it implies this pair as well. So like you can't have just this pair and not that pair, right? So yeah, right. But okay, but the overall question, however, that we were interested in is if you, I guess, yeah. I mean, like, does that fully characterize all of the? Yeah. I mean, like, we're trying to understand, I guess, a kind of combinatorial level. If you, like, as you increase in the dimension, well, in particular, like, how far away can you get from the input function? Okay, so let's just do the same thing that we just did, but for n equals 5. Right, we're gonna generate, like, oh, I just realized, yeah, it would make more sense to just make this say 0 as opposed to taking the absolute value. But anyway, yeah, like we sort the weights and then set the bias to 0 and we compute what the actual, yeah, okay. Alright, so let's look at n equals 5. Right, so it's kind of a similar thing, right? It's, right, also, how is this being, am I sorting? It looks like I'm not sorting. Oh, no, I am sorting. Okay, that's cool. Yeah, so the columns are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, sorted in a way that I don't quite understand. But that's fine. So, right. But, okay. But the overall thing we were going to try to figure out was that, this leftmost column is input identity. And then we're hoping to, and then it looks like, conjecturally, right, that this rightmost column is always going to be as far away, like as uncorrelated with the leftmost column as possible, like out of the set of canonical LTFs. And in particular, if you can, like, here you have like 16 rows that are purple, and you have 1, 2, 3, 4, 5 of those rows that are yellow. If you could have achieved 8 yellow rows, then you'd have zero correlation. And so then you could show that within the set of canonicalized LTFs, you can achieve zero correlation with the input identity function, albeit in like a very specific way. And so yeah, that's kind of what we were, that was the goal I was like, yeah, I'm gonna figure that out on live stream. And yeah, like, can we characterize this rightmost column function for increasing in, and then B, can we like get a bound on like how many of these rows can be yellow? But anyway, yeah, so we're gonna look at this n equals 5 setup, however. The rightmost column, right? So it's saying that which I guess is relatively rare or something. Yeah, but yeah, like, we're trying to figure out the set of implications, because it seems like it should be a orderly. So like, in other words, if I just told you, like, I have an n equals 5 canonical LTF, and it, the sum of the 3 smallest inputs is larger than the sum of the 2 largest weights, rather. Does that imply all of these other flips? I think it like does. Actually, I don't know. I mean, empirically it does, because there's only one function that, I don't know if you could, like, just directly deduce that, though. Yeah, so, okay, let's just look at it. Right, so we're saying, like, I think I don't need rule lines. Yeah, we're gonna like stare at binary inequalities. Well, I mean, they're not actually. I mean, they're not being interpreted as binary integers. Or, yeah. Okay. So anyway, I already forgot what I was talking about. Right. So we're saying you have this the two largest weights, right? Like the weights are leftmost is largest. And we're saying that those are smaller than the three smallest weights. Yeah, and then I guess we're gonna try to go through every other, like, yeah. Also, just to be, like, explicit, like, you know, like, a weight array that accomplishes that, you know, it's, like, not that hard to, I mean, you just pick a large, like, you know, like, 199, you know, 98, 97, 96, right? Like, if those are your weights, are there 5 of them? Yeah, so, like, you know, this is 199, the top 2, and the bottom 3 is, you know, like, larger than 199. It's almost 300, I would say, or something. Anyway, right? So, I mean, it's not crazy, you know, like, yeah. Okay. Alright, so what we want to do is say, like, does that... First of all, like, what about this guy? Here, we have... I mean, like, because... yeah, because this only occurs once, like, we're assuming that it implies, like, every other row. I mean, like, also in combination with, it's a, you know, like, we're in the set of canonical LTFs with, you know, positive sign sorted weights. Yeah, okay, but, like, does that imply this one, right? So this is saying, like, yeah, I'm gonna write that as it occurs. So, because, yeah, this is greater. Okay. Alright, so then I can look at the next row and be like, yeah. What about 0, 1, 0, 0, 0 is less than its negation, 1, 0, 1, 1, 1. Yeah. Okay, so, like, what's the, yeah, I mean, like, what's going on here? Let's also write that in the other way. 1, 0, 1, 1, 1 is greater than 0, 1, 0, 0. It's like, does this imply the bottom one? And it's like, well, okay, so it's the same dynamic. Like, you take, like, to go from here to here, you take the largest weight and you subtract it from the small side, so the small side is necessarily getting smaller, and you add it to the large side, so the large side is necessarily getting larger because everything is positive. Yeah, so that is a direct implication. Cool. So this implies this row. Okay, so, like, what if we flip this one? Yeah, that doesn't matter. Okay, let me get rid of that. We don't need that. So what we're doing is, like, we just flip that and do that. What are we doing here? Wait. Oh, man. Well, I mean, I don't know. You can give the interpretation here to go from here to here. You're taking the small weight and you're just replacing it with a large weight. And then here, you're taking the large weight and you're replacing it with the small weight. So, yeah, that's also implied. Yeah. Yeah. I don't know if there's this, like, is there a way to, like, is there like a finite number of, these things happening? Nobody knows. Okay, let's just, I don't know, look at this. So this is saying that 0, 1, 0, 1, 1, 0, 1, 0, 1, 1 is greater than its negation. You don't actually need to look at it. It's negation. 1, 0, 1, 0, 0. Alright, so does the top imply the bottom? I guess you could do the interpretation of like, okay, I'm taking this weight and I'm moving it up. So that makes that side larger. And then I'm taking this weight and I'm moving it down. So that makes that side smaller. Okay. Yeah, okay, let's go all the way down to here. So this is saying that 0, 1, 1, 1, 1 is greater than 1, 0, 0, 0. Is this necessary? Like, does this top imply this bottom? And again, I think it has the interpretation of you're taking the second largest weight, you're subtracting it from the small side, so it makes that smaller, and then you're adding it to the larger side, so it makes that larger. So therefore, this implies this. Right. Okay, what about, like, you know, going up here? Like, what about this one? I mean, like, we're saying, like, this one row implies every other row. It implies an exponentially many number of rows. That seems weird to me. Okay, so let's look at the other thing. 0, 0, 0, 1, 0 is less than its negation. 0, 1. Okay. Let me write that in the other direction. 1, 1, 1, 0, 1 is greater than 0, 0, 0, 1, 0. Right, and we want to go from here to here. So, I don't understand what's happening. You're subtracting these two and replacing with a smaller. Yeah, I mean, like, necessarily this single weight has to be smaller than, I mean, it's smaller than these two individually. So, necessarily this transformation is, it makes this value smaller. So that number's only getting smaller, so that's good. And then over here, it's the same transformation, but in the other way, like, because these two indices are the same, so that doesn't matter. So you're subtracting a small weight, which makes it smaller, which is bad, but then you're adding two weights that are guaranteed to be larger than the weight that you subtracted. So it's necessarily larger. So yeah, so like this one statement implies this. I feel like I'm confused in some area. I feel like I have various confusions. Let's just look at this guy. Let's look at that row. So it's 1, 2. Well, actually, I'm going to go the other way. It's 1, 1, 1, 1, 1. Is greater than 0, 0, 0. Well, I mean, that's just implied. Yeah, I mean, I guess, I mean, like, some of these are not. I mean, some of these are just implied by the canonical, you know, like, yeah. I mean, that's just necessarily implied. So, yeah. I think, I mean, like, this column is unique in that this input, like no other input, no lexicographically smaller input can be larger than its negation. I think that's true. So like for all n, I think you can like characterize this column as saying like yeah, like if you pick the lexicographically smallest input that can be larger than its negation, if it actually is, then that like uniquely determines the function. I mean that still seems highly conjectural. And then but then anyway, if you could demonstrate that, then it would then you would need to be able to demonstrate that, or I mean, like as n grows, like how many yellows, you know, are implied in the top half. Okay, so I'll just look at, I guess, like, yeah, like one more case. So this is the same thing for n equals 9, I would say. And yeah, again, we have like this extremal column where it's saying the sum of the last 5, the smallest 5, the 5 smallest weights, the sum of the 5 smallest weights is larger than the sum of the 4 largest weights, right? And then it's like, I guess that implies like everything else. And so then yeah, we didn't actually, let's see, where's the half? Okay, so this is the halfway point, and right, I don't know how many yellows that is. It does look like a lot. You could make a bound. An easy bound would just be, you know, that everything less than this has to be purple. Could you similarly have, no? Also, I mean, like, is it weird? Is it weird that this is purple? Let's look at that real fast. I'm gonna look at that and like do something else. Okay, we don't need this. Okay, we're in n equals 9 now. It's getting pretty big. Okay, so we have 1, 2, 3, 4. 1, 2, 3, 4, 5 is greater than 1, 2, 3, 4. 1, 2, 3, 4, 5. Right? And then we're concerned with this row. So this row is saying that 0, 1, 2, 3, 4, 1, 2, 3, 4 is less than its negation. So 1, 1, 2, 3, 4, 1, 2, 3, 4. Okay, yeah. Does this imply this? Or, like, is this, like this is not implied by the canonicalization rules. Right? I mean, like, if you could find 9 sorted numbers where the sum of these 4... Wait, could you? Oh, no. Yeah, I think you could. You could. Yeah. Right. Okay, but we have the further constraint that this is true. So, what's the interpretation here? Well, it's like, yeah, I mean, to go from here to here, you just take this weight, and then you make it big, so you're increasing the magnitude over here. And on this side, you take the big weight, and you make it small, so you're decreasing the magnitude. So yeah, this does imply that. Right. Okay, but that's like this row. You know, it's kind of like, why doesn't it imply like other stuff? Yeah.